Welcome back, everybody. We have a fairly tricky problem to do with specific and latent heat here of some liquid paraffin suitable for IB physics. And here is the problem. What we have is some solid pieces, which I've represented as one big 30-gram lump here, of solid paraffin at 42 degrees centigrade, and they've been dumped into 150 grams of liquid paraffin, which is at 240 degrees centigrade. In this case, it won't matter if you convert to Kelvin or not, because the intervals are the same size between temperature and degrees centigrade or Celsius and Kelvin. So the problem wants to know is when equilibrium is reached, as in there's no energy being transferred between the two objects in this case, then what is the final equilibrium temperature? If you fancy solving this problem, crack on, give it a shot. Otherwise, here's the solution. So what effectively is going to happen is the hot liquid paraffin at 240 is going to give some of the energy to do three things to the solid lump or lumps at 30 degrees. It's going to heat it up until it gets to its melting point. That would be phase one there. Phase two, it's going to change the phase of the paraffin. So it's going to turn from a solid into a liquid. And then any other energy it has left, it's going to use to heat up the paraffin, most likely somewhere above 47 degrees. And so you can kind of estimate roughly where it should be. So it's got to be a number somewhere between 47 and 240. And there's a lot more mass of liquid paraffin. So I'm betting it's somewhere around about 200 degrees. So let's have a look and see how we get on. Got the equations. And phase one, we are heating up. Phase two, we are using some energy to change state, increase the potential energy of the bonds and the kinetic energy. And then we are going to heat up from there as well. So it's really a case of energy equals energy plus energy. And where's this energy coming from? The liquid paraffin. So with our four types of energy, this is kind of what it looks like, where the 1, 2, and 3 are the solid paraffin, and the 4 is the liquid paraffin, which we're cooling down. Now, when we do a little bit of working around here, there's that first expression is changing the temperature using the data above, and I've converted into joules per kilogram per Kelvin. And that's raising from 42 to 47, so the change in temperature is 5. Then we need to change the state of 30 grams, which is 0.03 kilograms of the solid liquid, turning it into liquid paraffin. And then finally, we need to heat up the mass of liquid paraffin, well, that current mass of liquid paraffin into something above 47. And where's this energy all coming from? It's coming from the liquid paraffin, which is 150 grams of it, all the other data inserted there. And the final temperature is going to be below 240. So it's 240 minus the temperature. Running through the algebra after that is just pretty straightforward. You just got to be careful to multiply out everything inside the brackets by everything outside the brackets. Here's the next step that I took. We'll make sure everything with a TF in it for temperature final is on the left side of the equation. Working that through, dividing 72, almost 73,000 by 383, we get a final temperature of 190.3 degrees centigrade. There we go.